For our pendulum, we used a Rubik's Cube that had Velcro stuck to one of its sides and a tennis ball that had Velcro stuck to its surface.
The Rubik's Cube was hung from a table by a string. We made sure that the Velcro side of the Rubik's Cube was facing the tennis ball, which was thrown at the pendulum.
A yardstick was placed under the pendulum to calibrate length for the video analysis, and a red sheet was hung up behind the pendulum to provide a color contrast.
The mass of the projectile, which was the tennis ball, and the mass of the pendulum bob, the Rubik's Cube, was found using a triple beam balance. The mass in grams was converted to kilograms.
The velocity of the projectile before the collision and after was determined using tracker analysis to be 5.389 meters per second before the collision and 2.229 meters per second after.
The maximum height of the pendulum after collision was also found using tracker to be 0.198 meters above its initial position.
We calculated the conservation momentum, which theoretically should equal zero, by multiplying the mass of the ball by the velocity of the ball right before the collision, and adding it with the mass of the pendulum bob times the initial velocity of the pendulum to find the initial momentum, and set it equal to the final momentum, which was found by adding the mass of the ball and the mass of the pendulum, and then multiplying it by the velocity of the combined objects right after the collision. We then subtracted the initial momentum from the final momentum to find the change in momentum, and we got 0.0520 milliseconds.
In order to calculate if energy was conserved throughout the pendulum's motion once the projectile and pendulum collided, the maximum kinetic energy was set equal to the maximum potential energy. Since the kinetic energy was at its maximum immediately after the collision, it was calculated using the mass and velocity of the projectile and pendulum stuck together, and it was found to be 0.4227 joules. The maximum potential energy was found by multiplying the mass of the projectile and pendulum by the highest point of the center of mass above its initial position, and the acceleration of gravity to find that the gravitational potential energy at its maximum height was 0.3302 joules. Although theoretically the energy should be conserved with no difference between the maximum kinetic and potential energies, the energy decreased 0.0925 joules.
Due to the perfect inelasticity of the collision, there was a notable decrease in kinetic energy before and after the collision. Using the mass and velocity of the projectile right before colliding with the pendulum bob, the kinetic energy was calculated as 0.8220 joules. The total kinetic energy of the ball and pendulum moving together immediately after the collision was calculated to be 0.4227 joules. Subtracting the kinetic energy before the collision from the kinetic energy after, the results produced a decrease of 0.4593 joules.
Some key results that are determinant in the completion of this project was a small increase in momentum and decrease in energy.
Through this project, we learned how to execute and analyze a perfectly inelastic collision in the real world, and allowed for outside factors to come into play that had not been anticipated previously, including the twisting motion of the pendulum after collision likely causing error in the 2D analysis of motion.